Okay, hello and welcome everybody. Thank you very much for listening to my online talk as a part of the 5th Geometric Analysis Festival. Before I start, I don't want to miss to thank the overall main organizer, Hojo Lee, for his incredible work, and as well, more specifically, Fabian Rupp, who is the organizer of the section Higher Order Variational Problems in Geometry, to which this talk belongs, for his kind invitation to give a talk. What I want to tell you today about is reverse conformally invariant Sobolev inequalities on the spheres. This is a preprint that appeared last year, written together with my former PhD advisor Rupert Frank from Munich and Hanli Tang from Beijing. So at the risk of repeating some things I already said quickly in the introduction video, what is this talk going to be about? Very briefly, we shall be concerned with a certain variant of the Sobolev inequality, one of the most famous inequalities in contemporary analysis, certainly, which you can see written here in its fractional version on Euclidean space for any fractional exponent between 0 and s, that is for every fractional order of differentiation s. One has this inequality where a derivative L2 norm controls from above a certain LP norm of the function. When s is in this range, one knows essentially everything about the inequality, at least in this form. In particular, one knows the explicit optimizers and one knows the sharp constant. What I propose to look at in this talk today is what happens when we try to go outside this range. So what happens when we try to study orders of differentiation S that are larger than the space dimension. So of course, you usually know that in this setting, the right Sobolev embedding is not anymore measured in LP norms, but so you get better, you get embedded into a certain Maury space. But so what I want to ask is, does an inequality more like this also hold, where we really control the integral of some power of the function still by the Sobolev norm? So of course, this leaves wide open what this appropriate extension of the Sobolev inequality should be. And we will first have a look at this. This is precisely where we will take advantage of the setting on the sphere that I will introduce right away. And then once such an inequality is established, we can ask for optimizers and best constants and see if we can, as for the Sobolev inequality, classify the optimizers explicitly. I can promise you answers that you will hopefully find interesting. So there are some interesting phenomena going on. And so let's get started. My talk will consist of 2 parts. The first part, which might be slightly longer, will consist in an introduction where I will introduce all the objects that we will manipulate, tell you some known results, and then finally end up in the statement of our main result from our recent article and some discussions about it. Very briefly, what our result says is something quite surprising. Namely, we have some kind of a dichotomic in this non-standard range s greater than n half. Told you we will see that we have 2 different kinds of behavior according to these 2 subranges of s. In the subrange that is adjacent to the standard interval, we will somehow maintain the standard behavior of the inequality yet to be written, of course, whereas beyond this somehow pseudo-standard interval, things really get bad and the inequality, so to say, totally ceases to hold. So this is a quite intriguing thing to see. We'll get to see this in detail. And then in the second part, I will try to present some elements of the proof by particularly insisting on two structural features of the problem, namely its conformal invariance on the one hand, and the use of the diagonal basis of the spherical harmonics, notably as test functions in non-existence results on the other hand. So let's get started. I recall you that the Sobolev inequality that I wrote you in the most basic, or what I consider to be the most basic form, was on Rn. And as we shall see in a second, it will be helpful for the extension that I have in mind to transfer this to the sphere. This is possible because the inequality is conformally invariant. We have a conformal map, the well-known stereographic projection or inverse stereographic projection from Rn to the sphere, which is given by this explicit prescription here. And then, so this is all very well known. One can read this, for example, in Beckner's 1993 paper. One gets the following equivalent version on the sphere, which looks very much like the Sobolev inequality that we saw on the first page. Here there's the identical LP norm, which now, of course, is an LP norm on the sphere. We have the exact same best constant. And on the left side, the Laplacian, the fractional Laplacian, transforms into the following funny looking, at first sight, operator A to S, which we can consider to be a differential operator on the sphere. In fact, it is a certain complicated function. So you should read this in the in the sense of spectral calculus. It's a certain complicated function involving square root and gamma function of the Laplace-Beltrami operator on the sphere. So this is the right differential operator by conformal invariance that is involved in this Sobolev inequality on the sphere. So this is totally equivalent to the Euclidean statement, and therefore also the statement on the optimizer's transfers. And it turns out that, so this is even actually more natural on the sphere, namely the optimizers are given by, in particular, by this family of functions, which contains in particular the constant function, the constant functions if we take the theta equal to 0. But more generally, if we allow any theta of norm less than 1, this turns out can be recognized precisely as all conformal transformations on the sphere of the constant function. So this is really a classification result, because if the constant function is an optimizer, then certainly all conformal transformations are optimizers, and in particular there are no more. Seen differently, these functions really are, of course, for everything to be consistent, the stereographic transformations of the bubble functions that we saw on the first slide, which are optimizers in the Euclidean setting. So in order to tell you what we want to do, let's have a bit of a closer look on this operator A to S. So basically, it is this inequality now that we want to make sense of for higher powers of S, for higher values of S outside the standard range. So when we look at the operator, I mean, say in the standard range, first of all, by the definition, it's defined from the Laplace-Beltrami in terms of spectral calculus. So it has the same basis of eigenfunctions, namely the so-called spherical harmonics, which are by definition, for example, the eigenfunctions of the Laplace-Beltrami operator, whose explicit eigenvalues we know. And so by this formula, we can compute, by just plugging in the eigenvalues in the formula, we can compute the eigenvalues of the operator A to S. So this operator we know very well. But now this is nice because, I mean, when S when S is greater than n-half, which is the range that we eventually want to consider, then this argument of the gamma function, at least for certain values of L, will become negative. This may look weird, but it's in fact not a problem to well-definedness of this thing. I mean, this still gives a well-defined number because the gamma function is defined on negative arguments. It's just that it takes the value infinity on negative integers. But in that case, we can just set this quotient equal to 0, and then we have really a well-defined thing for everything, and we can define the associated operator that acts on spherical harmonics by the by multiplication with the eigenvalue given by this number alpha of L. We have an associated quadratic form, which in fact defines a norm equivalent to the standard HS norm on Sn. And so this A to S is nothing but, is really the same thing as this norm on the left-hand side of the Sobolev inequality. So this extension works fine. And then what do we do with the integral? I mean, I think I mentioned at some point in the introduction video, it's easy to see that when we take S greater than 2n, then this here ceases to be reasonable because it's not an LP exponent of an LP space really anymore, but this here is negative. But when we just write down the integral, then we get this funny looking thing here, where we take the integral of u raised to a negative power. So formally, at least, this minimization problem makes perfect sense and certainly extends the minimization problem from the standard Sobolev inequality. So mind you that despite the slightly different notation, what is written here, the infimum that we're taking here, is nothing but the infimum of this quantity divided by this quantity on the left-hand side. So when you're looking for a Sobolev inequality, you're trying to prove that the infimum of this quotient is strictly positive, with infimum given by this S, and this is what we shall wonder about in the following now too. And this quantity here to be minimized, which will have various behaviors as we shall see, I will always denote by this I to Sn. So this is something to keep in mind. As last small caveat before we go on, I hope you will find it reasonable. It's not exactly dictated, but it is very reasonable, and it will make for the nicest kind of results if we decide to minimize over positive functions only. So in the context of usual Sobolev inequalities, this never makes a difference. Minimizers turn out to be eventually positive all by themselves. Here we put this in as an assumption in the minimization problem from the beginning, that we're minimizing over positive functions only. This certainly helps a lot with a priori having this integral, which is now a negative power. So this becomes divergent if we approach 0 with having this well defined. So let us start by looking a little bit closer. So the real thing to understand about this minimization problem is really the behavior of the eigenvalues. So here there is the eigenvalues are given by the following quotient of gamma functions, both in the standard and in the non-standard range. But the thing that changes when we pass to the non-standard range is that the eigenvalues start changing sign, right? So when S is less than n-half, then the gamma functions take only positive arguments. So we have a quotient between two positive numbers, whatever this is, it is positive, the quadratic form is positive, definite, and so on. When this is not the case, then when the gamma function takes a negative argument, you can see this just by the recursion formula for the gamma function, then the functions will become negative, the gamma function might become negative. In fact, from this recursion formula that I said, you could easily see that the gamma function is, for example, negative between 0 and -1. Then it is positive from -1 to -2. Then it is negative again from -2 to -3 and so forth. And so what we have for the low-lying eigenvalues where L is not so small is small enough to have this argument here negative, we have that the eigenvalues really are alternatingly positive and negative as we increase the degree of the spherical harmonics L. So in particular, in general, we may have that this infimum I2Sn that we study is and will be in general a negative number. It's only clear in certain cases that it will be a negative number, for example, because we still have this constraint that we are only allowed to take positive test functions. But for example, if alpha 0 is negative, that is, if the spherical harmonics of degree 0, that is the constants, do give a negative eigenvalue, which is, for example, the case if S is just beyond n half, then we can plug a constant as a test function and receive a negative number in the variational problem. So in that case, we really have the infimum negative, or still even possibly at this point minus infinity. If S minus n half is an integer, we are back to the somehow exceptional case where the denominator here becomes infinity and then the eigenvalue is 0. So in that case, we have that all the low-lying eigenvalues are 0, and starting from some L, so the first L larger than S minus n half, will be positive. In this case, the minimization problem is really trivial because the infimum is 0, and it's taken on exactly by positive linear combinations of spherical harmonics living in the eigenspaces corresponding to these 0 eigenvalues here. So just for the purposes of illustration, looking at the lower half of this slide here, what does such an inequality look like then in the simplest of cases? So here I've tried to, for comfort, write this down in the form of a usual Sobolev inequality. So write out this infimum I2Sn in the form of a usual Sobolev inequality again. And in fact, in one dimension for S equals 1, we have this first order Sobolev inequality. So mind you that when n equals 1, the natural looking exponent S equals 1 is really already in the non-standard range. And then one has this inequality, which is due to I, Cho, and Y from 2001, who also proved that the optimizers are of the standard form. So this is remarkable, seen as a result on its own, because it gives the first piece of evidence that also outside the standard range we may have something nice. So we may have a Sobolev inequality that still holds, things do not go wild, and we also may have the classification that carries over. So recall that as we saw here, this is precisely the form of optimizers for the Sobolev inequality in the standard range, and they continue to optimize this slightly twisted Sobolev inequalities with negative powers and negative infima all over the place in this non-standard range. So there is hope that this is true for a larger range of S and N. So an intermediate step towards this result for every dimension for higher integer orders, for higher orders, but still confined to S equal to an integer, is the following important result by Hang from 2007. So he, in principle, develops this result, this classification result that we saw on the slide before, to higher orders. So what does his theorem say? when n is an odd number. So it's convenient to take n odd, because then the integers, the integer exponents to follow are such that that s minus n half is not an integer, because we saw that when s minus n half is an integer, we are in this exceptional case where everything is easy and nothing interesting really happens. So we prefer to be in the case when s minus n half is not an integer, and where we want to have s at the same time being an integer. It's preferable to work with this. So this is the only reason for the assumption that n is odd here. So what Hang's theorem says now is that when s is beyond n half but not too far, so when s is n half plus 1/2, or when s is 1/2 plus 3/2, then the result of HO and Y continues to hold. So we have the infimum equal to the best Sobolev constant. This I didn't write this here, but this is also nothing but the expression for the best Sobolev constant written here, evaluated for the non-standard choice of S and N now. So this leaves us again with the negative argument of the gamma function. But as we saw, this is no problem, just that it might give a negative number, as it did here, for example. So in that case A, we really keep having the behavior of the standard Sobolev inequality. And then the second and completely new observation of Hang was that very surprisingly, all of this breaks down when you go further away from the threshold n-half. So when you keep s an integer that is n-half plus 5/2 or larger, then Hang proves that the infimum is not achieved, and a fortiori that there can not even be a local minimum. So in that case, the inequality or the minimization problem, let's say, because it precisely does not really turn into an inequality for sure, the minimization problem ceases to behave more or less completely like the Sobolev inequality. So this is Hang's result, and this is really the place in the literature to which the question that we are trying to answer with our main result are attached. Namely, so what is the interest now when you observe such a crazily divergent difference in behavior as in Hang's theorem between cases A and B? One would of course like to know where the transition between these two behaviors takes place precisely. But in order to determine this, you of course have to admit all the values of S. You have to admit a continuum of S in order to really locate the transition. Because even if Hang's theorem considers quite a general setting, his limit is that he considers, let's say, isolated points. So he knows that he has a point with standard behavior, and then the next point where he looks, he has a non-standard behavior. But it would be really of interest to determine at what value in the continuum there's such a transition. And the second question concerning part B, which Hang didn't answer in his theorem, is what in the case where it goes bad, what is the value of the infimum? Do we still have a finite infimum that is maybe only not achieved by functions, or is the infimum really minus infinity there, and thereby precluding any inequality to hold from holding in that case? The answer that we got is here. So this is exactly the same type of theorem as Hang's before. It has a part A and a part B, a part A where it goes well and a part B where things do not go well. With the difference that it is now, as I said, valid for every fractional exponent S larger than n-half, where we, for the purposes of statement, exclude the easy cases of the integers for which everything is clear by the remark that I made before. And where we additionally answer in almost every cases the second question here about the value of the infimum in the bad case. So let's see what this says precisely. So this says, what this says is that the transition is at n½ plus 2. This was not clear from Hang's result because he has n½ plus 3 halves and n½ plus 5 halves. So you might have guessed that it is the nicest number in the middle between these two, but this is what our theorems now really prove. So if S is less than n½ plus 2, then we are in the standard case. The infimum is of our minimization problem is the Sobolev constant, and the optimizers are the usual suspects, the conformal factors. If S minus n½ is larger than 2, then I2 as n is not achieved. We can prove by a first simple argument imitating that of Hang. So this is what Hang said. But we can say more by an independent argument. We realize that at least in the case when n is greater or equal to, then the infimum is actually equal to minus infinity. So there is no inequality at all in that case. Okay, so some more comments. I think the first two bullet points I already mentioned in presenting the theorem. So when S minus n½ is an integer, then we have 0 eigenvalues, and the classification of the minimization and even the classification of optimizers becomes trivial. And this infimum equals minus infinity was not known before, even for integer s, as I already said. Of course, the obvious question is what happens when n equals 1. This should be actually the simple case. Yes, it should indeed be simpler than the higher order cases. It's just that we construct test functions which are not appropriate for some reason when n equals 1, and for the moment we don't know how to fix it. We do not expect that there is a different behavior, but at the moment we have no proof when n equals 1. Slightly more subtle remark that one can make for fun here is on this condition u is greater than 0, which I already mentioned in the usual Sobolev inequality. It doesn't play a role, because even if I optimize over functions of any sign and sign changing functions, optimizers turn out to be, the global optimizers turn out to be positive anyway. In this non-standard range, it's somehow different, and this is interesting, because so when I impose this condition u greater than 0, then I recover that everything behaves like the normal Sobolev inequality. So the infimum is exactly the Sobolev infimum. On the other hand, when I drop this condition, I mean, I could restrict to not necessarily positive function that only require maybe that this integral be finite. That means that they don't vanish to very, very high order near 0. And I would still get finite quantities in the minimization problem. But these functions realize a lower infimum than only the positive functions. So I mean, restricting to the class of positive functions really makes for a jump in the infimum. So this is something that has already been observed by Hang, actually. That, for example, in the case s equals 2, n equals 1, which is a case where one really has the Sobolev infimum greater than 0. But if you plug in something that changes sign, like a first spherical harmonic, you get something that is well defined and everything, but which is negative, but finite negative. So this would still make sense. Okay, we are thus almost at the end of the first introductory part. I would like to conclude this with 2 more slides on some background topics since we have time, which can be seen as also as extended comments on the statement of the theorem. So the first thing I want to talk about is the topic of reverse HLS inequalities. So it is really in that spirit, or as an allusion to these reverse HLS inequalities that we chose to call the family of inequalities that we prove reverse reverse Sobolev inequalities. In case you wondered where the reverse is, for the HLS inequalities, this is clearer. So as a reminder, the classical HLS, Hardy-Littlewood-Sobolev inequality, proved in its sharp form by Lieb, says the following. This is also conformally invariant, can be formulated on the sphere and on Rn equally. So here's the version on the sphere. It says that this double integral with the convolution with the integral kernel x to the or omega to the mu for some negative power mu is controlled by, from above now, by the LP norms of the involved functions. The optimizers are the same kinds of guys, the conformal factors, same kinds of guys as in the Sobolev inequalities. In fact, this is not a coincidence that the optimizers are the same, but as is well known, the HLS inequality in the standard range is really the dual of the Sobolev inequality, in the sense that they are equivalent to each other and equivalent to each other via LP duality. So a brief sketch of the argument might be given as follows. So admitting the HLS inequality, let me prove the Sobolev inequality, so still in the standard range. And this simply relies on the fact that the operator that is involved in the Sobolev inequality, the operator A2S, its inverse, that its Green's function, is given by this integral kernel here that is precisely the one up to a constant factor that comes from the HLS inequality. And then what can I do with this information? Well, I can take, for any function g, I can take the scalar product between, fix some f, take the scalar product with some g. I introduce a to the 1/2, a to the -1/2, take this apart with Cauchy-Schwarz, and use the HLS inequality. And if I then maximize over overall f for overall g for a fixed f, and use the definition of use the dual definition of the LP norm, then I really recover this inequality here, which is nothing but the Sobolev inequality. With some more effort, I would even check that the constants are the same, must be the same, and the optimizers must be the same. But now what is interesting for our purpose is that there is also a result for a non-standard range of so what is now the free exponent in the inequality is now the mu. There's also an extension of this to a non-standard range of mu, namely for all mu greater than 0, so which corresponds to s greater than n½ in the Sobolev world. There, interestingly, Doe and Zhu in 2014 proved the following HLS inequality, where the same kind of double integral, just now with the positive exponent mu, controls from above something that looks like LP norms on the right-hand side, but in fact are not, because when mu is greater than 0, then these things are less than 1. So these are not actually LP norms in the usual sense, but I mean the corresponding integrals of f to the q with q between 0 and 1. The optimizers are still the same, and this holds for every mu greater than 0. So in particular, and what is funny is that for this reverse HLS inequality, there is no non-existence phenomenon like the one that Hang observed and that we explained more in detail in our theorem. So even if so as a funny conclusion of this discussion is that even in the standard range, the Sobolev and the HLS inequality are completely equivalent by this duality argument. So you see easily that this duality argument breaks down outside the standard range. And indeed, there these inequalities really become something completely different. So to end this first section, a second bit extended comment on geometry, namely more precisely about curvature. So for this, to recover this geometric setting, we consider Sn as a Riemannian manifold equipped with the simplest standard round metric G0, induced by the embedding in Rn plus 1. And then we may view every given positive smooth function on Sn as the datum of another metric G of u given by this prescription, which is pointwise conformal to G0. Associated with such a metric, and in fact, in terms of u, we can express then a certain curvature quantity, the so-called Q curvature of order 2s, which makes sense to define for every s, given by this expression here. So this is a vast generalization of something more manageable and more concrete when s equals 1, namely when s equals 1 and n is at least 3, then this quantity is nothing but the scalar curvature. And we are back in the setting of the famous Yamabe problem. So in that sense, considering the Q curvature problem really amounts to studying a generalization of the Yamabe problem, which has encountered quite a lot of interest in recent years. So with all these geometric notations at our disposition, we can rewrite the same minimization problem that we have been studying, which was to minimize 0 over 0 over functions u greater than 0, the quantity that I write now in terms of the integral over the measure on Sn given by the new metric G mu. And then when I plug in the definition of the curvature, then I realize that the minimization problem becomes equivalent to maximizing overall metrics Gu conformal to the round metric and parameterized by smooth positive functions u, the integral of the total Q curvature divided by the volume to a certain power. So differently put, since we know that the maximizer, that the minimizer of our minimization problem by our theorem is the constant whenever we are in the good range, and also when s minus n half is any integer, possibly outside the good range, 0, 2. We can just rephrase our theorem in geometric terms as follows, by saying that among all metrics pointwise conformal to G0 in this sense, and satisfying the volume constraint of having the same, giving Sn to Sn the same total mass as the standard round metric, then this round metric maximizes the total Q curvature, that is the integral over the Q curvature among all of those metrics, provided we are in one of the cases that I just said, namely s minus n half is either between 0 and 2 or is an integer. So this finishes the first part. Thank you very much if you stayed on until now. There will be a second part of my talk in which I will discuss a bit some aspects of the proof. Would be glad if you connect again.